Good morning, students. Today we will discuss different types of buses in a power system. In a power system, the buses are meeting points of various components. The generators will feed energy to the buses and loads will draw energy from the buses. In the network of a power system, the buses become nodes, and so a voltage can be specified for each bus. Therefore, each bus in a power system is associated with four quantities, and they are real power P, reactive power Q, magnitude of voltage, and phase angle of voltage delta. The buses of a power system can be classified into following three types based on the quantities specified for the buses. The table shows the quantities specified and the quantities to be determined for each type of bus. First one, the load bus or PQ bus. The bus is called load bus when real and reactive components of power are specified for the bus. The load flow equations can be solved to find the magnitude and phase of bus voltage. In a load bus, the voltage is allowed to vary within permissible limits. Next, the generator bus. The bus is called generator bus when real power and magnitude of bus voltage are specified for the bus. The load flow equation can be solved to find reactive power and phase of bus voltage. Usually for generator bus, reactive power limits will be specified. And the last one is the slack bus. The bus is called slack bus if the magnitude and phase of bus voltage are specified. The slack bus is also called as reference bus for the load flow solution, and usually one of the generator bus is selected as the slack bus. Now we will discuss the importance of slack bus. Basically, the power system has only two types of buses, and they are load and generator buses. In these buses, only power injected by the generators and power drawn by the loads are specified, but the power loss in transmission lines are not accounted. In a power system, the total power generated will be equal to the sum of power consumed by the loads and the total power loss in transmission line. But the transmission line losses can be estimated only if the real and reactive power of all buses are known. The power in these buses will be known only after solving the load flow equations. For these reasons, the real and reactive power of one of the generator bus is not specified, and this bus is called the slack bus. It is assumed that the slack bus generates the real and reactive power required for transmission line losses. Hence, for a slack bus, the magnitude and phase of bus voltage are specified, and the real and reactive power are obtained through the load flow solutions. The load flow analysis. The load flow study is the analysis of power system under steady state condition. That is when the system is working under balanced condition. As the system is balanced, we can do the analysis by using per phase network. The main information is obtained from a load flow study are the magnitude and phase angle of the voltage at each bus and the real and reactive power flowing in each line. The load flow solution also gives the initial conditions of the system when the transient behavior of the system is to be studied. The load flow study of a power system is essential to decide the best operation of the existing system and for planning the future expansion of the system. It is also essential for designing a new power system. Let us form the basic load flow equations using Y-bus matrix. The node basis matrix equation for an n-bus system is given by I bus equal to Y bus into V bus, where I bus is the source current matrix of order n by 1, Y bus the bus admittance matrix of order n by n, and V bus the bus voltage matrix of order n by 1. Let us concentrate on the pth bus in the system. Let IP be the current injected to bus P and Vp the voltage of bus P. From this matrix we can write IP equal to Yp1 V1 plus Yp2 V2 plus etc. Ypp Vp plus etc. Ypn Vn. Now we will split all the terms into three areas. Let us consider a 10 bus system here. Therefore n equal to 10, and we are going to concentrate on the fifth bus. So P equal to 5. So the first term in equation number 1 is the terms corresponding to bus number 1 to bus number P minus 1, that is here bus number 1 to bus number 4, that is the terms related to bus number 1, 2, 3 and 4 comes under the first area. Then the second term, it is the pth bus, or the terms related to pth bus, that is here in this case the fifth bus. And the third term, it consists of the terms related to P plus 1 term to n, that is 5 plus 1, 6 to 10th bus, that is 6, 7, 8, 9 and 10. So just we have classified the same equation into three categories, and that is our equation number 1. Now let SP, PP, QP be the complex power, real power and reactive power of the bus number P. Therefore I can write SP equal to PP plus JQP. Also the power in terms of voltage and current, we can represent it as SP equal to Vp into Ip conjugate. Equating these two powers, we can write Vp into Ip conjugate equals Pp plus JQP. Now taking conjugate on both sides and rearranging, we will arrive at equation number 2 as Ip equal to Pp minus JQP divided by Vp conjugate. Now equating the RHS of both equation number 1 and 2, we will arrive at the basic load flow equation as shown. As per K2 syllabus, we are having three methods for load flow analysis: Gauss-Seidel method, Neutron-Raphson method and fast decoupled method. And you can expect problems, direct 10-mark problems from Gauss-Seidel method, and they will ask you to write the theory part or the procedure for finding load flow analysis for Neutron-Raphson method and fast decoupled method. Now we will discuss the Gauss-Seidel method for load flow solution in detail. The Gauss-Seidel method is an iterative algorithm for solving a set of non-linear load flow equations. The basic load flow equation discussed earlier can be rearranged as shown in equation number 3, and this forms the basic equation for load flow using Gauss-Seidel method. The variables in the equations for P equal to 1, 2, 3, etc. up to n are the node voltages V1, V2, V3, etc. up to Vn. In Gauss-Seidel method, an initial value of voltages are assumed and they are denoted as V1 of 0, V2 of 0, etc. up to Vn of 0. On substituting these initial values in the equation and by taking P equal to 1, the revised value of bus 1 voltage, that is V1 of 1, is computed. The revised value of bus voltage V1 of 1 is replaced for the initial value V1 of 0, and the revised bus 2 voltage V2 of 1 is computed. Now replace the V1 of 1 for V1 of 0 and V2 of 1 for V2 of 0 and perform the calculation for bus 3 and so on. The process of computing all the bus voltages as explained above is called one iteration. The iterative process is then repeated till the bus voltage converges within the prescribed accuracy. In view of the above discussions, the load flow equation can be written in the modified form as shown. Vp of k plus 1 equal to 1 by ypp into pp minus jqp divided by vp of k conjugate minus sigma q equal to 1 to p minus 1 ypq vq of k plus 1 minus q equal to p plus 1 up to n vq of k, where k is the iteration value, n is the total number of bus, and p is the bus number which is at study. Now in this equation, to compute the k plus 1th iteration value of bus p voltage, the k plus 1th iteration values of voltages are used for all bus less than p, and kth iteration values of voltages are used for all buses greater than or equal to p. It is important to note that the slack bus is a reference bus, and so its voltage will not change. Therefore, in each iteration for a generator bus, the reactive power is not specified. Therefore, in order to calculate the phase of bus voltage of a generator bus, we have to estimate the reactive power from the bus voltages and admittance as shown. Rearranging the basic load flow equation by keeping the reactive power term only on the LHS, we will arrive at the final expression for checking the reactive power limit of the generator bus as Q of P k plus 1 equal to minus 1 into imaginary part of Vp of k conjugate into sigma q equal to 1 to p minus 1 ypq vq of k plus 1 plus sigma q equal to p to n ypq vq of k. Also, for generator bus, a lower and upper limit for reactive powers will be specified. In each iteration, the reactive power of generator bus is calculated and then checked with the specified limits. If it violates the specified limits, then the reactive power of the bus is equated to the limit violated and it is treated as a load bus. If it does not violate the limits, then the bus is treated. Let us now do one problem on Gauss-Seidel method. For the system shown, determine the voltages at the end of first iteration by Gauss-Seidel method. Take acceleration factor alpha equal to 1 and bus specifications are given in the table. Here we can see a 4 bus system represented by 1, 2, 3 and 4. And for each bus, P, Q, V and angle and its remarks, they are also specified. So the first bus, you can see the voltage magnitude and its angle is specified. So it can be considered as a slack bus. Now the second bus, P, V and limits of Q is specified. So actually P and V is specified along with the Q limits. So the second bus is actually a PV bus or a generator bus. Now the third and fourth bus, its P and Q is specified and V and delta is unknown. So it is regarded as a load bus or PQ bus. Now in this figure, all the elements are in admittance per unit. And the first step is to form the Y bus matrix as we studied earlier. Here you can see it is a 4 bus system, and the Y bus will be also having the order of 4 by 4. And the first element Y11 can be obtained by adding all the admittance connected directly to the first bus. That is, in this figure you can see one line is connected between 1 and 3 and other line is connected between 1 and 2. So just by adding the admittance of these two lines, you will be getting 1 minus J5 plus 1.2 minus J4, that will be 2.2 minus J9. And the second element Y12 or Y21, it can be obtained by taking the negative of admittance connected between bus 1 and 2 or bus 2 and 1. That is, in this case, negative of 1 minus J5. Similarly, find all the values of Y bus matrix. After that, the initial voltages of load bus are assumed as 1 plus J0. That is, we will assume a flat start for load bus. And for slack bus and for generator bus, the specified voltages are used as the initial values. That is, V1 of 0 equal to V1 of 1, which will be equal to V1 of K, that will be equal to V1, since it is a slack bus, and it is specified as 1.06 angle 0 or 1.606 plus J0 per unit. For generator bus, the angle is unknown. We have to assume 0 initial angle, and the magnitude is specified as 1.04. So V2 of 0 for the generator bus equal to 1.04 plus J0 per unit. And in case of load bus, that is the third and fourth bus, we will assume flat start because we don't know the voltages at that bus. So we will assume it is 1 angle 0 or 1 plus J0 per unit. Also, for generator bus, the specified powers are considered as positive powers. But for load bus, the specified powers are considered as negative powers. For first iteration, put K equal to 0. In each iteration, the slack bus voltage need not to be recalculated. In each iteration, the reactive power for generator bus has to be calculated and checked for violation of the specified limit. If the bus 2 is a generator bus, and to calculate its reactive power Q2, we will substitute P equal to 2, K equal to 0 and N equal to 4 in the Q equation. Since the bus 2 is the generator bus, we will substitute P equal to 2, that corresponding bus number. And for the first iteration, K equal to 0, second iteration K equal to 1, third iteration K equal to 2, and so on. And N is the total number of buses. So when you are substituting, you can find the Q2 of 1 calculated. That means reactive power of second bus on the first iteration. And while substituting, the value will be 0.1456 per unit. Now for the second bus or the generator bus, the reactive power limits is specified in the question itself. Now say in that question, let the reactive power limits be 0.1 to 1. 0.1 to 1 be the limit, and you can see the calculated value of Q2 of 1 is 0.1456. It stays within the limit, so there is no violation of reactive power limits. Therefore, this bus can be treated as a generator bus. Therefore, P2 equal to 0.5, Q2 equal to 0.1456 and V2 of 0 equal to 1.04 plus J0. Now we have to find the angle of voltage of the second bus. So we will put some temporary value with magnitude as the magnitude specified, that is 1.04, and we will calculate the value of angle delta 2 of 1. So in this equation we will substitute P equal to 2, K equal to 0 and N equal to 4, that is V2 of 1 temporary, and we will find the value as 1.0496 angle 2.05. So the required angle delta 2 of 1 is 2.05. Therefore, at the end of first iteration for bus 2, we have obtained the voltage magnitude as well as the angle as 1.04 angle 2.05 per unit. The bus 3 and 4 are load buses. The voltages of load bus are also calculating using the same method. Just substitute P equal to 3 and P equal to 4 in the equation for voltage, and you can find the values of V3 of 1, that is voltage of third bus for the first iteration, as 1.0031 minus J.0154 per unit, and the value of V4 of 1, that is the voltage of bus 4 in the first iteration, as 0.985 angle minus 1.04 per unit. So at the end of first iteration of all the buses, we have obtained the results of voltages at each bus as shown. You can see V1 of 1, that is the voltage of first bus at the end of first iteration, is 1.06 angle 0, and this value will not change because voltage 1 or bus 1 is a slack bus. Its voltage and angle will not change at any iteration. Now the second bus, it is a generator bus. 1.04 magnitude was specified in the question, and we have found the angle 2.05 from the equation, Q equation. And voltages for bus 3 and 4, that is the load bus, we have obtained as shown. Now this is the end of this problem, and we will discuss what happens if the Q limits are violated. Now let us consider a case of reactive power limit violation. In the same example, we will now change the reactive power limit of generator 2 or bus number 2 as 0.2 to 1. Previously it was 0.1 to 1. Now it is changed to 0.2 to 1. So previously we have calculated the Q2 value and we have obtained it as 0.1456. So you can see that the lower limit 0.2 is violated. The obtained value is less than the lower limit. Therefore now the generator bus is going to be treated as a load bus, or PV bus is going to be get converted to a PQ bus. Therefore the reactive power generation for bus 2 is fixed at 0.2, that is the lower limit, and the bus 2 is treated as a load bus for the first iteration. Now the voltage value at the initial case, that is V2 of 0, is now 1 plus J0. Previously we have taken the value which is specified in the question, 1.04. Now in this case, since it is now a load bus, we have to go for flat start, that is V2 of 0 is 1 plus J0. But the P and Q values are considered as positive for bus number 2 because it was previously a generator bus and the values are get converted to PQ bus. So the P and Q values are not taken as negative, similar to other buses, other load buses, but here we will assume P and Q as positive values itself, and the remaining P and Q values of other load bus given, that is bus number 3 and bus number 4, we will give negative values. By substituting the values in the main equation, voltage equation, we can find the voltage at the end of first iteration for the each buses, that is bus number 2, bus number 3 and bus number 4. So let's start with bus number 2. Just substitute P equal to 2, K equal to 0 and N equal to 4 in the equation, and we'll be getting V2 of 1 equal to 1 by Y22 into P2 minus JQ2 divided by V2 of 0 conjugate minus Y21 into V1 of 1 minus Y23 into V3 of 0 minus Y24 into V4 of 0. Here we will substitute P2 equal to plus 0.5 and Q2 equal to plus 0.2. And V2 of 0, it is not 1.04 as in the previous case, it is 1 minus J0, since the generator bus is converted to a load bus. And finally we will be getting the value of voltage at the end of first iteration as 1.0551 angle 2.06 per unit. Similarly, we can calculate the voltages of other two remaining buses, that is bus number 3 and bus number 4, as similar to the previous case.